let's talk about how that triangle similarity is used in our activities. Now, in your activity, you were asked how you knew that these were similar triangles. Well, the main thing that we'll often see in triangle similarity is angle-angle. We're assuming that both the tree and the person are being measured at a right angle to the ground. Now, where's the other similar angle? It's the angle of the sun. We assume the sun is far enough away that when it shines and creates shadows on these, it creates the same angle. That's where we can say these are similar triangles, because we end up with angle-angle similarity. One, because of how we measure heights, and two, because of the sun being so far away that the angle generated by the shadow has to be the same. Now, you may be curious what this means about what the correct answer is. Well, we can use both our scale factor and internal factor. I can look at this and say, hey, what do I have to multiply 2.5 by to get to 37.5? Well, let's see. I believe that ends up being 15, if I'm thinking correctly. Yep, that's 15. So I multiplied the 2.5 by 15 to get to 37.5. So to get to the 1.5, I'd multiply that by 15 to get the tree height. And so that gives me 22.5 meters. I can also use internal factors. To get from 2.5 to 1.5, I multiply by 3 over 5. And it just turns out that 37.5 times 3 over 5 is also 22.5. Now let's look at how in the squawking chicken example we have similar triangles. Here we have similar triangles by, once again, angle-angle. You may see one of the angles in assuming the people are standing up straight. That's how we measure height. Now the other one is actually right here. Now, why are these angles the same? It's the reflection principle I mentioned on the paper. The formal term is angle of incidence, or where the angle at which a ray of light hits a mirror equals angle of reflection. So, for example, if I have someone who is 100 centimeters away and they are 173 centimeters tall, I'm going to make the woman in this image be that because I'm male. Well, how far away do I need to stand? I haven't done this in a while, but I believe my eyes are about 100 and, oh, what was it last time? We'll say 168 centimeters. Well, once again, I can do either scale factor or internal factor. Now, what's the scale factor here? What do I need to do to go from 173 to 168? That's not one we know off the top of our heads, but we can take advantage of fractions. I know I multiply by 168 over 173. So I'm going to do the same on a calculator to that 100. I'm going to take 100 and multiply it by 168 over 173. So let's see, what is that? 100 times 168 over 173, and it ends up being about 97.11 centimeters. Similarly, I can say, what did I do to 173 to get to 100? Well, I multiplied it by 100 over 173. So if I multiply 168 by 100 over 173, I'll get the same number. And if you're not sure with these crazy numbers, think of it this way. With the scale factor method, to figure out this length, I did 100 times 168 over 73, or 173, excuse me. For the internal factor, I did 168 times 100 over 173. Notice the same number. We can get the internal factor method just by switching the 100 and the 168, which we can do by the commutative property of multiplication. It's going to be the same number. No matter how you calculate it, it ends up being 100 times 168 over 173. All right, I hope this was helpful. Please contact me if you have questions.